everyone, good morning. We are going to get started by continuing from where we left off. And Lee, you had a job to do, but since I now know what that job is, I'll just do it anyway. We were going to talk about awkward notation. So let's suppose that we were being asked to find partial derivatives, and that's not a big issue. Let's suppose that the function was called x cubed plus xy squared. I'm taking a really baby question. Now we have two versions, two notations that indicate the first partial derivative with respect to x, right? And these are the same thing, so it's pretty obvious that the answers are the same. Now, if your function is described as z equals instead of f of xy, then the notation is really not that different, right? It's zx and dz by dx, right? The subscript notation and the delta notation are very similar looking and are for sure interchangeable. Would you agree? It's pretty obvious what's going on. So where does the awkwardness happen? The awkwardness happens when you do more than a first derivative, when you do a partial second, or for that matter, third derivative, and then things get really messy. So let's suppose I'll pick a different fella this time. Let's do that guy. All right. So start off with first partial derivative. No biggie, right? And we did this at the end of yesterday. That's a second partial derivative, isn't it? And what does that mean? Well, that means you now take this answer, right? And then you differentiate it, partial derivative, with respect to y. So 2xy cubed basically is like 25y cubes. You multiply by the power, and you reduce the power by 1. And e to the y is e to the y. I think subscript notation is pretty obvious, the order that you do things. In particular, don't you do x first and y second? Great. Now, if you were being asked to do that guy, that would count as a third partial derivative. And would you agree it makes sense that you would basically do the x first, then the y second, and then do another y? So you would take this fella here and do a partial derivative with respect to y. And the order is x first, y second, and y third. Well, let's look at what that ends up being. If we use the delta notation. So I'm going to use the exact same guy. Now in delta notation, the first partial derivative with respect to x is written that way. No biggie. Pretty obvious. Everything's cool. Now the awkward part. Suppose I wanted to do this partial derivative, right? X and then y, right? X first, y second. What that is saying is that you want to do a partial derivative with respect to y of that guy. I mean, that's essentially what this is, right? X is first, y is second. Now, do you see that when you write it this way, it's a bit clunky? But that's not how it's eventually written. It gets written this way. And that guy is the same fella as this guy. But the problem do you see that the variables are written in the reverse order? In other words, that guy's first and that guy's second, but as you read it, doesn't it have the y first and the x second? That's what makes that awkward. So if you, for instance, were being asked to do this fella, what would you start off with? Which would be the first variable to do your partial derivative with?
X,
And then?
Y, and then the other Y.
Yeah. Do you see how that's backwards? I mean, backwards because in our culture we read from left to right. I guess if you were an Arab or I think the Jewish culture, I think they read from right to left as well as the Arabic. So for them, that might actually be more sensible, and that would be the weird looking one, perhaps. But you see that the notation is a bit clunky, because it would be really nice if these were written in the same kind of order that you do things. And this is the same as doing X first, Y, and then Y. So you just have to live with that, because I can see a situation where you're given a function and you're being asked to find the derivative of that function, right? And you have to look at this and you have to say, well, what order should I do it in? X, Y, Y, or Y, Y, then X. And you know, you could have issues with your answer not being done in the correct order. There is a little caveat to this, which is really cool. So I'm now going to tell you right now. Still can't figure out how to spell the guy, but I'm going to have another shot at it. Let's put an X in his name this time. The guy Claro. You remember the guy who went and said that as long as your function, put a Z there, that it doesn't matter what order that you do the two derivatives. Remember, I think I did it as ZXY and ZYX, right? Which actually is the wrong way around, but you know what I'm saying. If they're equal to each other, or they will be equal to each other when the function is continuous, right? That's what Claro said. He also says the following, which is really cool. Provided the function, and it could be, you know, written that way, or it can be written the equivalent that way, provided it's continuous, all variable orders give, oops, a little bit more room, the same result. Let's put that in English. Suppose I'm going to do a fourth partial derivative. If the function, you know, the z equals, if that's a continuous function, right? If you did a picture and it's a nice flowing hill, he is saying the following: zxy xy is the same answer as xxyy, is the same answer as yyxx. It doesn't matter what order you do them, the answer ends up being the same. So the caveat is, remember this awkward notation where it's sometimes difficult, especially in this format, to know who you should do first, who you should do second, and who you should do third. As long as the function is continuous, it won't matter. Won't you get the right answer even if you decide to do them in the wrong order? Right? It'll still be the same final answer. So this one is saying, suppose you're doing a fourth partial derivative, twice with x and twice with y. You could do it in this order, you could do it in that order, you could do it in that order, and you end up with the same answer. That is pretty amazing property. That French guy was on top of it to even, you know, find that. That was pretty amazing. I guess most of the time you do it by, you know, you just do a lot of derivatives and you start noticing, hey, how come they're the same answer? You know, what is going on here? Is that just luck? Was that just random luck? And then you try lots of weird and wonderful functions, and most of them end up working, and you think, nah, it's not just coincidence. And then you go and you try and prove it to formula just to make sure that you've got a good foundation. It's really cool. So as long as your function is continuous, if you're doing multi-partial derivatives, you're okay if you do them in any order you like. So here is an example of a special puzzle. That's meant to say x, by the way. E to the power of x cubed, the sine of e to the x cubed, plus x y cubed. Right. If I asked you to find this partial derivative, or I might write it down like that, it's the same thing, right? Well, technically, I should write it like that. If I asked you to find that second partial derivative, and you decided to do one with x and one with y, right? So we know that Clairaut, this is a mess. Let me get this out of the way. Distract me. Let's just do it as if I hadn't written it. Suppose then I gave you this function and I said, find me the second partial derivative, where one of them was x and one of them was y. And I tell you that this function is continuous. There are two orders that you could do it in. Agreed? Couldn't you do the y first and the x second, or the x first and the y second? And according to Clairaut, won't they be the same answer? So it means you can choose either one. But in this very special case, I know which one I'm going to do first. The x or the y first?
Y.
Agreed. Give me a good reason.
Because it'll eliminate the first term, which is a mess.
And it's just going to be a 0, isn't it?
Yeah.
So if you do this function and you do it with respect to y first, doesn't this just get you 0? Because everything's got x's in it. And over here, you get 3x y squared. And then you can do the x's. Now, do you see, by choosing to do the partial derivative, the multi-partial derivative, in one specific order, rather than the order that you were given or the order that you had a choice, do you see how it's reduced your workload by an awful lot? So I can imagine that that might be a very useful thing, especially if the function is decidedly ugly. Right? If one piece of it, like this piece, is full of x's, I would probably try and make that one go away as quickly as I could. So that's a very interesting property. Now I'm going to show you another one. Again, this is really properties that help you reduce your workload in finding partial derivatives. So Clairaut's, the one we just finished, says, look, if you're doing multi-variables, right, x, y, actually, third, fourth partial derivatives, we'll make the assumption that the functions are continuous, then just decide what order you want to do it in. And sometimes one order is less work than the other. This next one is going to look at a trick you can use in symmetric functions. Here's an example of a symmetric function. So what makes a function symmetric? Well, it has the property that if you turn the x and replace it by a y, and you take the y and you replace it by an x. In other words, if you switch places, you have the same function. Well, let's imagine I did that. It would become y squared plus x squared over the sine of y plus the sine of x. Now, algebraically, can't I rearrange those two additions and those two additions? And do you see that it is now the same fella? If you sketch a symmetric function, can you imagine that if you look at it side on with the x-axis facing you, and then side on with the y-axis facing you, won't it look exactly the same? You know, it's got a symmetry to it. Cool? Now, here's an example of a function that is not symmetric. If you switch the x's and y's, isn't this not the same thing? So how do symmetric functions help? Well, if you're being asked to find the first partial derivative with respect to x, and then the first partial derivative with respect to y, or any partial derivatives, you can use one answer to predict the other without doing the math. Let's show you. Here's a symmetric function. E to the power of 2x plus 2y plus x cubed plus y cubed plus xy. Pretty messy function. Let's do its partial derivative with respect to x. Well, first, would you agree this is a symmetric function? Can you tell just by looking that the x's and y's are perfectly matched and balanced? Does it make sense? Right. So it is a symmetric function. So let's do the partial derivative with respect to x. Okay, I'll work at the end first. This guy gets you plus y. This guy gets you nothing. This guy gets you 3x squared. And this guy's a bit messy. You're going to get e to the 2x plus 2y times something. What is the partial derivative? What's the extra bit that's going to go here? It's like the chain rule. Essentially, what's the derivative of 2x plus 2y with respect to x?
2.
Just 2. Now, you notice that I've just done the answer as a partial derivative with respect to x. Now, can you imagine this was a lot uglier than that, right? So you fight your way through and you get a good answer and you're happy with it. I can now tell you what the answer with respect to y is without actually doing it again, just by using this answer. And how do you do it? You just switch the x's and y's around. So 2 to the e, technically 2y plus 2x, but that can be rewritten as 2x plus 2y. Won't the 3x squared become 3y squared? And won't the plus y become a plus x? Are we cool? I'm making this up. Let's suppose we had a function and we got its triple derivative with respect to y. Right, it took us forever and a day, but we finally got it. So pretend there's some function out there and I've done the triple derivative, and this is what you ended up with when you were finished. Right, that's what it looked like, for argument's sake, right? I do not want to have to do the whole question from scratch. First derivative with x, second derivative with x again, third derivative with x again, right? I don't want to do that if I can avoid it. If this function was symmetric, and we'll assume that it is, shouldn't we be able to use this answer to predict that answer? And this answer then becomes y x cubed sine of y cubed x. Do you see how your workload has been reduced significantly by just using property of symmetry? Are we good? Now, pretend, I know this is very unlikely, but just pretend, a new question, right? Pretend that this derivative here was x cubed y plus y e to the xy, right? Just for argument's sake. And the function was symmetric. Oops. And the function was symmetric. What's that, guy?
The same thing.
Same thing. In fact, being symmetric doesn't really help, right? Because won't we just use Clairaut? So if you know it's correct, if you know it's symmetric, right? I guess it's just a special case of Clairaut's property, right? But symmetric allows you to do more situations, right, where you can work on. Have we any issues right now? Are we cool with what we've covered? We're looking good? Okay. I thought I would do, kind of working backwards again, that I do some partial derivatives, just first partial derivatives. But this time we're going to do them with rather uglier functions. And so this is my first one. X squared plus y squared over 2x, take away y. And we're going to find the partial derivative with respect to x. What method would I have to use to find this fella? Product rule, quotient rule, chain rule? I mean, what kind of rule is kind of guaranteed with this question?
Quotient rule.
Quotient rule. So that's going to be f dash g, take away f of g dashed all over g squared. And this whole piece here is f, and this whole piece here is going to be the g. And remember that f dashed actually means partial derivative with respect to x in the context of this question. So if you take the top and do a partial derivative with x, you get 2x. If you leave the bottom alone, you get that. If you leave the top alone, you get x squared plus y squared. And if you differentiate the bottom with respect to x, you just get times 2. And the whole thing in the bottom ends up looking like that. So I'll multiply or distribute, in this case, 4x squared take away 2xy, take away 2x squared, take away 2y squared, and it's over 2x minus y squared. And what does that look like when I finished? It looks like it's going to be 2x squared, take away 2xy's, subtract a y squared, all over 2x take away y squared. And I don't think I can do much better. That's probably as good as that's going to get. Comfortable then with a quotient rule? Product rule, we've done a lot, chain rule. So let's try this fella then. I'm really just going crazy now, you know. You probably won't see this question, or if you do, you're only going to see one. Would you agree this question has got a lot of different things going on? Let's suppose I'm asking you to find the first partial derivative with respect to x. Product rule, agreed? Product rule. Would you agree that this fella is also going to involve a chain rule. So why a chain rule? Because it's something being squared, and that something isn't simple, right? It's got some stuff inside it. So we are going to have to recognize that this little piece is F, and this bigger, uglier piece is going to be G. And the product rule, which is the kind of major framework, goes here. If you differentiate this guy, you get 3x squared, and you leave the ugly mess alone. And then you leave the x cubed alone, and now the killer, g dashed, right? Which basically is, what is the derivative of this thing, partial derivative, with respect to x? So it's basically a chain rule, something squared. So that's going to get you 2 lots of this something, technically to the power of 1, but also times the derivative of this with respect to x, and the partial derivative of this with respect to x is y. Take away 2xy. Oh, okay. I've got this ugly mess plus this ugly mess, and we really should try and make it as good as we can. I can see an x squared as a common factor. I can see an xy times a yx squared as a common factor. I think that's all the good common factors, so let's see what I'm left with. 3 lots of this fella, plus 2, one of these x's, that's used up, and a y take away 2xy. So I now have an x squared, an xy take away yx squared. Distribute this, you get 3xy times take away 3yx squared. This fella gets you 2xy take away 4x squared y. And I have an x squared. I have this fella. That and that combined, so I get 5xy. Take away this guy. Take away that guy. Let's check it. 5, 3 of them, 4 of them. Right. Here's a puzzle for you, or a question. Is that as factored as much as it could be? Because you really should be writing your answer in its best format, right? I call it style points. So, and can this be improved upon? Right? Is there anything you can do with xy take away yx squared?
You could pull another x out there to the front.
Right? Could we pull out a y as well while we're at it? Agreed? So let's pull it out. That'll leave me with 1 take away x. 5xy minus 3yx squared minus 4x squared y. Is there anything we can pull out of there?
1x and 1y.
So we'll pull that out. And that'll leave me with 5. Take away 3, use that or use that. So take away 3x. I just noticed something. Yes, and I'm glad I noticed it right now. And they shouldn't have combined them earlier on. So let's see what our final super duper finish is. An x, and that gets me 4. A y and a y gets me y squared. A 1 minus x, and a 5 take away 7x. Now, that is significantly different from this question. And isn't it much better looking as far as factoring goes? Can you imagine why this might be more helpful? Suppose I wanted to know when this partial derivative was equal to 0. If you factor this thing as best as it can be, isn't it much easier to solve the problem? When will this be 0? Well, I could tell you right now. Won't it be 0 when x is 0? Won't it be 0 when x is 1? And won't it be 0 when x is 7/5? Oh, and won't it also be 0 when y is 0? Do you see then that there are 4 possible places where this derivative would be 0? If I left it in this top format here, I think it would be much more difficult to find all these solutions of when it is 0. So the argument for why you should make things look pretty is because it's not uncommon for you to take a partial derivative and have to find out when it's 0. And if you don't factor the heck out of it, you're going to have a lot of problems solving that. I mean, I'm not saying you couldn't, but I've got a good idea that you might miss one of these 4. Are we good? Any questions? What I'd like to do now, if I can, hopefully I may not have set it up because that's me. Of course I didn't. Okay. I'm going to go in and look at some WebAssign questions. And as we scan through the partial derivative guys, if you come across one that you don't feel comfortable with, then I'll do something like it to try and help you. Okay, just getting this set up, so if you can just be patient for a few more moments, you should be ready. Come on, expand. That's good. Okay, why am I seeing the answers? I don't want to see the answers. I think the word here is I'm having technical issues. I'm going to have to go back out and go in. Try it this way. No. What the heck are you doing? Okay, we got it. Finally figured out what the heck I was doing wrong. Right, so I'm going to go into the homework questions. We can have a look at those. And here goes. Right, there's what, 21 questions altogether. In questions 1 and 2, you're being asked to find these 2 partial derivatives. Basically, you find the partial derivative with respect to x, but then whatever it is, you replace the x with 2 and the y with 7. So when you're finished, that'll be 14 and that'll be 12, or whatever. Right? Finding a partial derivative of what, a polynomial, I think that's pretty straightforward. Me personally, I wouldn't do the x comma y. I would just call it f subscript x, but I guess they do what they like. Here's a function, x and t. I guess you can change the variables. Are we okay with finding partial derivative that looks like this guy? A little fraction guy? Go with that one? Is question 7 okay, or do you want me to do something like it?
I wouldn't mind if you went over how to do that one.
Okay, I'll pick one similar to that. I'm going to go through a couple more just in that way I can kind of build up a kind of group of questions.
Just a quotient rule, right?
It's going to be a quotient rule with some, how do you deal with some weird extra letters, A, B, C, and D in this case. Question 8 would be a quotient rule, wouldn't it? You agree? Quotient rule is a fraction. Well, here's a guy, I don't think I've done this yet. In fact, I know I haven't. Do you know this is a function of 3 variables, x, y, and z? And so I guess it could be called w equals that. Now, if somebody says do a partial derivative with x, with y, and with z, do you agree it's pretty easy to add the number of variables a function can have? So in this case, if I wanted to do a partial derivative of this guy with respect to z, which would be the answer here, wouldn't I just say, okay, x cubed y z squared, with respect to z, don't you just differentiate the z squared bit? And so you would get 6x cubed yz. Does that make sense? And then if you did 2yz with respect to y, with respect to z, when you get 2y. Okay, and there's same thing. Interesting. You're still going to find the partial derivative, but once you're finished, you're going to replace the s with the 0 and the t with the 9. Do you feel comfortable about doing a partial derivative with respect to t of this weird thing? T times e to the s over t. You feel comfortable with that? We good? It'd be a product rule essentially with a little bit of a chain rule, because s over t might cause some issues. And I'm going to do implicit. So the one I'm going to do will be like question 12. I'm just going to make up my own version of it. Okay. And right, that's some tricky stuff we'll do later. Second partial derivatives, I think we're cool on those. Some more second partial derivatives. Hey, I finally found out how to spell Claros.
People have been writing it in the chat for the yesterday and today.
I can't, yeah. Unless I physically go out of everything and click on the chat, I don't get to see chat. So if anybody, for instance, somebody in my previous class said, someone has asked a question in chat, if someone could repeat that verbally to me, I'd be able to tell. So did you find out how to spell it by just looking up the bloody book, or did you already know how to spell this guy? You looked at the book to find out how to spell it? Homework, whatever. Okay. Right, and there's going to be a Laplace one here. So this will be my version of 19. Okay. And basically partial derivatives. Okay. Let's return now and show you some of the stuff that I haven't covered or are a little bit trickier. Right, so first one. We have a function that is essentially a fraction where A, B, C, and D are considered constants all the time. So they'll never be variables. And you're being asked to find the partial derivative with, say, respect to x. So when I look at this function, what I see is that top is going to be called f, and this bottom piece is going to be called g. And so I recognize that as quotient rule. That's probably the first thing you should ask yourself. what technique am I going to use to get this partial derivative? And your answer is going to be quite limited. Power rule, product rule, quotient rule, right? That's the most likely. Right. If you do a partial derivative of ax plus by with respect to the variable x, this by term is 0 because it's just like 5y or 10y. And this ax is like 2x, so a is basically what you get. You then leave that guy alone. Then you leave the top alone, and you differentiate the bottom. Partial derivative with respect to x gets you c. And then the bottom gets squared. For style points, which is what I use to make it look pretty, I would never leave something as ugly as this. I would at least try and see if I can make it better. So if you distribute the a through those two terms, and then you distribute the c through those two terms, you get that. And two things kill each other off. And we now have c dy take away bcy over cx plus dy squared. Let's go for some more style points. Anything else you can do here?
You could factor out a cy from the top.
I think that's as good as that's going to get. Agreed? Yeah, nothing to do with this question, just curious to me. If I wanted to know when is this derivative, when is this ever going to be equal to 0? Won't it be 0 when y is 0? Because the bottom's never going to have an effect, right? If something's 0, it's the top that makes it 0, not the bottom. If the bottom's 0, you get undefined, so that's no use to you, right? Also, a rather curious thing, if d is equal to b, won't this be 0 all the time? So if d is equal to b,
I think in the third line up, that should be an ADY.
Yeah.
ACY
Yeah.
here?
No,
Um,
the
ADY.
C-
To the left.
Okay,
Yeah.
I'm here. What did I screw up?
it
One
should
line
be
down.
ACX plus ADY.
Oh,
Nope,
I
nope,
gotcha.
go to the left.
Here?
No, no,
No,
no,
no, no.
to the left. Okay, one more
Yeah.
over. There you go. That should be
It
A.
does say ACX.
No, and then it should be ADY instead of CDY.
Okay, so that's what I was
The
going
A
to do.
distributed through.
I gotcha. Okay. I'm going to go ... and you lot fix it.
Yep.
Y'all caught that deliberate mistake? It's actually not that hard to fix. I should fix it because they still kill each other off, so that's good news. So it's going to be ADY take away BCY over CX plus DY squared. And I can still pull out the Y, just not as nice a result. So this will be 0 when Y is 0, which is still true. And if AB is equal to BC,
AD is equal.
AD, so if they two multiply together are the same value as these two multiply together, then the answer is 0 all the time. I have no idea why that's the case, Because if you make this product the same number as that product, maybe what happens is that you just basically end up with a number. You know, the top line's just 2 times the bottom line, that kind of thing. That's probably what that means. Okay. Well, that one was harder than it should have been. Now, this is a new technique. Well, not really new, because you know it from Calc 1. Implicit differentiation.
Are we gonna do the chat for today's?
We are? Oh God, look at the time. Let's do the chat now, because we might not have time to do it after. So you got a minute to do the chat. Has anybody got a bad joke while we're doing the attendance? Okay, here's a very quick one. Do you know those kind of phrases that people give? Here's one. If at first you don't succeed, don't take up skydiving. Will that one work? Okay. Different. Yeah, that'll do. Here we have essentially our normal function. But normally, wouldn't you write it as z equals a function of x, y? But it has been jumbled up. So we are going to find, using what's essentially called implicit differentiation, we're going to look at this guy and we are going to find that partial derivative. So let's see how it works. You basically take each piece and, oh God, can I look? Let's make that number 20, just make my life easier. 20. So, partial derivative with respect to x of x cubed is 3x squared. The partial derivative of 3y squared with respect to x is 0, isn't it? Now, what about 2z squared? Well, the partial derivative of 2z squared with respect to x, this is where the implicit thing kicks in. Can you remember doing it in Calc 1? Y cubed would get you 3y squared dy by dx. You know, y squared would get you 2y times dy by dx. Think of that the same way. If you differentiate this with respect to x, you will get 4z times dz by dx. Does that make sense? It's exactly the same kind of process that you used way back in the day, right? Now, what is the partial derivative of 10 with respect to x?
0.
0. Now, I know it's a long time ago, but when you did Calc 1, didn't you then have to take this guy and solve for dz by dx? So that's all I'm going to do now. I'm going to subtract 3x squared from both sides. I'm going to then divide both sides by 4z. And there is the partial derivative dz by dx. And if you wanted to do the partial derivative dz by dy, wouldn't it be a very similar looking process? And if somebody asked you to find that, which would be really weird, the answer is in fact, isn't it 1 every single time? So you'll never be asked to find that one. But you will be asked, perhaps, to find the zx or the zy. Do you want to, I know I only have like seconds left. Do you want to look at another implicit, or are we good for today? We're good for today. Right, Leah, I'm giving you the job. Not that you end up doing it, but if I give you the job, it'll remind me that I want to start tomorrow with another implicit, and then we want to look at solving one of the wave equations, which is what this is. And then that's about it. Have a nice day, everybody. Have a good joke for tomorrow. I'm fed up telling you my jokes. I want to hear some fun jokes as well, because I've heard all my own jokes. So I need you to give me something new. Okay, well, bye-bye, guys. I'll see you.
Bye.
Thank you.
Bye.
See
See you
you.
tomorrow.
Bye.
Have a great day.
You too.